Hello, everyone. Today I'm going to present our work on designing explainable attention guide iris presentation attack detector. This is joint work with Arun at Michigan State University. What is a presentation attack? A presentation attack entails presenting a biometric sensor with a fake or deliberate altered biometric trait in order to fool the system. Presentation attack can be launched using printed iris, contact lens, and artificial eyes. In order to circumvent or deflect such attacks, we need to come up with presentation attack detection solutions. The literature, most of the times, they use convolution neural networks, and it can operate on either geometrically normalized iris image or unnormalized iris images. But all aforementioned methods, they do not use the attention modules to enhance the pad performance. Generally, attention mechanism can be roughly classified into two different types. One is a channel attention module, another is the position attention modules. Here, we give a summary of existing attention mechanisms used in the literature. Some works have used the channel attention module alone, but most works they consider to combine the channel and the spatial attentions. For our proposed method, here is our given flowchart. We call our method as attention guide iris presentation attack detector, which is short for AGPAD. So our proposed AGPAD improves both the generalization and the explanation capability. Here, we give the flowchart. Giving an iris image, it first imports to a backbone network. After that, we apply PAM and CAM to the convolutional feature maps. Then we fuse the outputs from those two different attention modules. In the end, we perform the flattening operation and input into the binary classifier. First, let's describe the concept about the position attention modules. For a given feature maps A, we will first input to the different convolutional operations in order to compute this position attention map. So this position attention map is used to measure the position dependence among the feature maps. After that, we need to multiply this position attention maps with the input feature maps in order to get the refined feature maps. And we also have to consider short connection since we need to add back the input feature maps A. So here is the overall flowchart to compute the position attention modules. Given the input feature maps A, first it is input to the convolutional blocks to obtain another feature maps B and the second feature map C. Then we can perform the reshaping operation to transfer the feature map of the B and the transpose operation as well. After that, we can simply multiply the transposed feature maps B with the feature map C to obtain the position map, which is also a two-dimensional image structure. After that, we can multiply the position attachment map with the input feature map D to get the refined feature map. Next, we are going to describe the channel attention module. So the channel attention module mainly, we still have to compute what we call the channel attention map Q. So the Q relies on the self-attention maps. So here the channel attention map Q is used to measure the channel dependency among the feature maps. And we also have to consider the short connection here, since that we have to add back the original input feature maps A. So here we give the overall flowchart for these computations. For the given feature map A, first, we still perform the reshaping operation and the transpose operations, and then we multiply back with the input feature map A. After that, we apply the softmax operation to get the channel attention map. And then this channel attention map will be multiplied with the input feature map A to get the refined feature maps. So after we obtain both the position attention map and the channel attention map, there are different ways to fuse them together. The first choice is that we can perform an algorithmized summation to fuse those two different modules. Second, we also consider to sequentially combine those two different attention modules. That means we first apply the channel attention modules, and then we apply the position attention modules. Let's present some experimental results to show the advantage of our proposed methods. We evaluate the proposed method AGPad on two different datasets. The first dataset is called a JHU APL dataset. And this dataset is mainly used for testing purpose. So we have collected a large number of training datasets, and this training dataset is not overlapped with the testing datasets. And this testing dataset is further divided into two different sessions. The first dataset is called JHU1, and the second testing dataset is called JHU2. And they are collected in different sessions. And as you notice from this figure, the quality from the JHU1 is much worse compared to the quality in JHU2 dataset. Since we have seen a lot of occlusions and the blurring effect associated with JHU1. Another dataset we are going to test is a public benchmark dataset called Live Detect 2017. And we will follow exactly the same protocol as the computation. In order to perform a fair evaluations, we have utilized different metrics. The first one is the ROC curve, and we report the true detection rate at 0.2% false detection rate. So that's the metric that we used on the JHU APL datasets. For the experiment results on the Live Detect 2017 computation, we follow the same protocol such that we use the BPCER and the APCER. The first experiment result is that we run our proposed method AGPad on both the JHU1 and the JHU2 with different backbone networks. As you notice that the DenseNet backbone network gives the best performance. And here we also show the fusion results for all the three different backbones. Especially on the JHU2, the fusion results gives the best performance. So here is our table results. As you notice that with the DenseNet backbone network, we obtain 100% accuracy on JHU2, but we only have like 72% accuracy on JHU1. That means JHU1 is much more challenging compared to JHU2. As you notice that the paired performance could vary with the nature of different presentation attacks. Here we show the experiments on different presentation attack types. As you notice that the contact presentation attack type is the most challenging one, and this is the contact types that we need to pay much more attention. Next, we also want to show what's the impact of different fusion mechanisms for the attention modules. So previously we have discussed about the sequential fusion and the parallel fusions. And generally we have observed that the parallel fusion performs slightly better than the sequential fusion. And the hierarchical fusion, that means we extend from the parallel fusion, but trying to extract the features from different layers. And we notice that the hierarchical fusion performs much better in the challenging scenarios as observed in the JHU1 dataset. We also perform an aberration study to show the impact of the attention modules. Basically, we evaluated results on using the PM module alone and the CAM module alone. So we noticed that if we just use the PM and the CAM, we can get a much better performance compared to the baseline results. And of course, if we consider both the PM and the CAM together, that gives our best performance on both GHU1 and GHU2 datasets. So our work also wants to present some results on the explainable visualizations. In order to give the explainable visualization results, we use the graded CAM visualization schemes. So the graded CAM works by throw the gradients back from the class output into the convolutional layers in order to get the maximized outputs with respect to the class informations. GradCAM can be used to highlight the important regions that correspond to a particular class predictions. Compared to other visualization schemes, such as series maps, feature visualization, or invert image representation, GradCAM provides a much simpler way to visualize the importance of different input regions with respect to predicted class. Here, we show the GradCAM visualization results before and after we apply the attention modules. The second row gives the results without using attention modules, and the third row gives the results after we apply the attention modules. Clearly, we can notice that after we apply the attention modules, the GradCAM starts to focus more on the cylinder regions. We also present our visualization results on the pattern detections. So we apply the iris detect first, get the cropped iris, and then we input the cropped iris to the presentation attack detectors. Here we show the visualization results on the detections with respect to different PA types. In order to compare with existing methods, we also run our method on the public benchmark dataset, which is the Live Detect 2017 computation dataset. That dataset contains results for both known and unknown presentation attacks. As you know, for our proposed method, we compared against 3 benchmark algorithms, and overall, our proposed method gives the best performance. To conclude our work, first, we propose a novel attention-guided CN framework for iris presentation attack detection that enables both generalization and explainability. We run the experiment on 2 different datasets and show the effectiveness on both known and unknown presentation attacks. Last, we show the visualization schemes in order to explain the performance of the proposed network. We also want to thank our sponsor of the IAPA for sponsoring this project. Thanks for your attendance. If you have any questions, please feel free to ask. Thank you.